Was. It's too much these days. So, relevant to this, I did an experiment. Sirius in literature V magnitude is blue by about 0.03, 0.04 magnitudes. So I had this idea that's because the rapid rotation has A star 0. And so if you take slow rotating A0 stars, Sirius, so I think the hypothesis is right. Using sort of unselected A0 stars for the 0 point, we can walk ourselves off to where the 0 point is actually
Actually, yeah, you've got to buy one of these. See the effective temperature.
Time is Sirius is blue, like a 0 point. Me, I ran a 3-day Miri TV, which is and when it's your turn to talk, bring your laptop up to the all the problems with connections and so on is vanished.
Oh, okay. Is that, it's the heritage there, that doesn't mean after like the.
You don't have the instruction on the side, in addition to everything else.
Named after the telescope that foundation.
Okay.
Yeah.
Last week I was imagining what if they were doing jackhammers.
It's thank you.
Problem used to be
I know Greg from school.
with construction, but when one of those went overhead, you just stop.
Grad school. Second. First grad school.
Did you degrees? Wait, or did you do like a master's?
Master's and PhD.
These are on duty.
You wrote John.
Yeah, I was across the street.
Yeah.
All right, we're good.
We're good.
People are starting to trail in.
Yeah.
Thank you.
It's damn loud. I can yell at the top of my voice, not really.
For
Graduate.
Think one of David Mazurka, which is tabletop.
Oh, that's probably better.
You have smaller.
That's funny. That's a bummer.
Really, really small.
Cafeteria.
So those devices, you could buy just Sabre stages that be sufficient. 8K. So that's really on USB.
Yeah.
Plugs right in.
Yeah.
Probably wouldn't X or an 8.
Probably the most popular thing.
The tabletop will be the physical size.
Just for 0 point masses.
Just like
I wouldn't say close to.
It's also
I'm not ready to give up.
the whole table has
I want to do.
around.
There's 0 magnitude.
It's
Stand up. Right, we.
Actually, occasionally this said, oh, nobody can read this. These glasses. I have these progressives.
Get from.
But I think what's still.
Also, it's 0 points and convert your impedance per second.
Zero magnitude flux density. This would be. Way that behind.
That's the magnitude for most of them.
Do a linear array. Telescopes that are like off to the side.
Ask questions, right? No, it's just we're trying to do the same stuff.
George, I'm just asking questions.
It'll make sense.
Just asking questions.
Used as workshop. 60 feet. Why when they come over?
But, you know, like, you could say you.
Okay. Since it's Kevin, they get 13. There's a. Any of us know? Yeah.
It's a good idea. I mean,
Tough for you.
I was like, who would be crazy enough?
Oh, is that what happened? That's why.
we're working on
Who showed up like? Right before that's gonna be.
I'm not 100%
Operators for new.
Okay, you're here, but you're not quiet. You've met only one of the requirements. Okay. Okay. I want to introduce this topic with a little story. Can you hear me? Yeah.
So, pay attention.
So we were just discussing with Kevin why Harold Johnston didn't use Sirius, and I wondered about that. And I think it's because Sirius from Arizona gets only, it's minus 16, so it's way off the zenith. And Vega goes right overhead, so we can get good air mass correction. So it's total accident of where Harold Johnston set up his photometry that we even think about Vega as a 0-point standard. And with that introduction, take it away, Kevin.
I trust people can hear me properly. Yes? Okay. The topic is the JBST magnitude system. This is the work of the JBST Absolute Calibration Group, which has been led by Carl Gordon since 2016. Many people have been involved, but the four that I consider the most prominent, so I put them on here, are names that we've seen lots of times already or heard from lots of times already. Okay. Start with what we are actually measuring and where we go with that. Fundamental imaging calibration, which Carl mentioned on his talk, was you take what we measure, which is the ramp slope in analog to digital units per second, and we transform it first to mean surface brightness over the system response in megajanskys per steradian, and then you can do photometry on the source and get a mean flux density in Jansky. And so you get these units in our level 2 and level 3 pipeline products from JBST. And if we understand our throughput properly, then we get nice values that are valid for any spectral shape of objects in our images, which is good because we don't know what those spectral shapes are. I would contend that we need to switch to standard magnitudes, though, when comparing photometry either between the filters, say on a given instrument, between instruments on JBST, and more particularly, if we start to look at other spacecraft or ground-based surveys or whatever, because these averages have a lot of filter-dependent information in them. We'd like to remove that to some degree, although forward modeling would be more precise if you want to go for really high precision. And if you use standard magnitudes properly, we'll remove most of this filter-dependent idiosyncrasies of these measurements. Maybe not all, but a lot of it. So for example, you can look at a star in one of our calibration fields. It's marked on the image there. It's been observed by NIRCam and NIRIS. And these filters that you see in the table that are the same filter in the different instruments, because it's really 3, have somewhat different, though only slightly different, flux densities coming out of our pipeline. So there's about a 3.5% difference between what is supposed to be the same filter. Now you might think 3.5% is not so bad. You can try to correct for it or whatever, but which you can, but this is the best possible case. If you wanted to observe something in our filters that are near the equivalent to Y's W1 and W2 and made this kind of comparison, you'd be 10 or 12% off, which is a rather more serious situation. And the standard magnitudes will help you with this by taking some of that idiosyncrasy of the individual throughputs of the different instruments out of your values. And of course, these are the magnitudes defined by having the average A0 star between two filters have the same magnitude, or sorry, the average of a sample of A0 stars to get the same magnitude. So you have to have a survey of some sort. So with 2MASS or WISE or Gaia, you have lots of stars. You can do this. When Hubble went up, though, they didn't do that. Hubble, of course, is not a survey instrument, telescope. It decided to look at one star, and they picked Vega and said, we're going to define Vega as magnitude 0 in all the filters. And this was entirely unprecedented, I believe. And this is what they've used ever since. You can see at the bottom there the magnitudes from the original Johnson and Morgan paper to define the UBV system, for example. And you see there's a small offset of a few hundredths of a magnitude. But what's more of a concern is you're picking one star instead of an average. You better hope that that star is somewhere near typical for the group that you're dealing with. And of course, we know now that that's not even remotely the case. But anyway. So we thought about using Vega for JWST because we also are not a survey telescope. But when we started discussing it, it was clear that this was not a good idea. This has been alluded to by George in his talk already, but I have the same kind of information. It's much too bright to observe in our telescope, which is bad. If we lay that aside, it has a dust ring that contaminates the photometry. We might be able to resolve it out separately, but we can't observe it, so that's not going to help. There's also this near-infrared excess, which is probably not going to be resolved out. And we're still, even if that wasn't bad enough, it's a pull-on fast rotator. There's this very nice paper by Oftenberg et al., 2006, from the CHAR array. They took a lot of interferometry. They reconstructed the disk image of Vega. So that's from their paper on the right-hand side here. The top one is what they estimate we see Vega from a lot of detailed interferometry. There's a large brightness variation from the center of the disk to the edge, and that is not limb darkening. That's a greater than 1,000 degree temperature change from the pole, which is near the center of the image, to the equator, which is on the edges of the disk. And the bottom is their reconstruction of what you would see if we could view it equator on. And also, Vega is a Delta Scuti variable star. There's a paper by Fernie, 1981, which I have seen, which says that there's some variability. On top of those other ones, that's not a big deal. And just to add, the biggest problem for us about this being a fast rotator is we're using a model to extrapolate from the optical to the infrared. We've got lots of observations in the optical. We like to extrapolate, but a one-dimensional model is not going to be able to accurately deal with this complexity of temperature across the disk. So this is all bad for us. So we started to think about what to do, and okay, now this, oh, there it is. Okay. We thought that Sirius would be a better choice. And this has been proposed before, for example, Engelke, Price, and Kramer, for example, in 2010. Of course, we're going from bad to worse in terms of brightness, but Sirius is otherwise really good for our purposes. It is an A0 star. If you trust Gray et al. 2003, which I certainly do. It is a slow rotator. It has a mild AM characteristic, but we can allow for that in our modeling. It has no dust excess, no stellar wind, and the companion, the famous white dwarf, is too faint to cause issues at our wavelengths, although if you went to the ultraviolet, that could be a concern. I was surprised to find that there's no interferometric disk image of Sirius the way there is for Vega, but there is a reasonable amount of interferometric data that is all consistent with standard limb darkening. So everything looks good, except that we can't observe it. Well, we'll come back to that later. The paper by Ricci et al. 2023 made analysis of the photometry and got a value for the K-short filter for Sirius. We need that because we need a way to hook into the standard system. And since we can't observe it ourselves, we have to take it from some other place. So if we've got that, you can compare Vega and Sirius. So here's some magnitudes just taken from the literature. And I didn't cite the sources for all of them because in some cases I can't find the sources, like in the Bright Star catalog. Who knows where they got it. But in the last column, you can see the differences between Vega and Sirius. It's the Vega's magnitude minus the Sirius one. And you see a significant change from the optical UBV as we go to, say, J band, and that's part of our wavelength range, so this is bad. If you standardize on Vega, you'll get one set of results, and if you standardize on Sirius, you'll get a somewhat different set of results, so you'll have color terms, essentially, between the systems. This is because Vega is a fast rotator, and Sirius is not, and there's a sort of bimodal distribution of ACE-type stars that shows up in a lot of cases, and so actually neither of them is good as an average of all the A0 stars. But we're going to have to forge on anyway. Okay, how do we define our magnitude system? Since we have to do it all theoretically, we have to adopt the stellar atmosphere model. So we take a model from CalSpec, this particular file. We calculate the mean flux density values for the filters the same way we would if we were going to observe this as a photometric standard. But in this case, we don't compare it to an observation. We take the values we get in average Janskis and assign it this magnitude minus 1.395, which is the 2 mass K value from the paper by George et al. And then so we offset down by this factor of 3.6141 to get to 0, and you get values like the ones in the table, which are the values for the nearest filters. We simply take those values and say, by definition, that's the 0 magnitude flux density. And there's no way to check that directly with our photometric calibration. So this is, at some level, entirely independent of our photometric calibration, which we don't really like to have. Again, I'll come back to that in a couple. All right, so we do that, and this is done for all the instruments in JBIS-T. You go into the pipeline, it gives you magnitudes back in the level 3 products. For imaging, whoops, went too far. Okay, problem is, in the pipeline source catalog, this is called the Vega magnitude. The reason being that all the programmers who were writing that part of the pipeline were veterans of HST, and we're familiar with this term. Well, this is an assumption on my part, I have to say. They didn't tell me this explicitly, but so they put the thing in there. I asked them to change it, and they did not. Oh, well. But these are not Hubble-style Vega magnitudes, and if you compare them in our overlapping wavelength range, you're probably going to see moderately significant offsets in the values because of the 2 different stars being used. So we have the oddity that our Vega magnitudes have nothing to do with Vega at all. All right. So are we finished? Can we just give up and rest on our laurels for some period of time? Well, no. We have an issue that we are basing our system on something we can't observe. So what can we do? We'd really like to have a 50th magnitude A0 star that is also unreddened so we can observe it with our filters. Well, we can't, but there's a couple of things we can think about. There's going going to a fainter A0 star. So this star BD plus 60, 1753, which is a standard used by Spitzer. And it's not somewhat fainter than Vega and Sirius. It's down around V of 9.5 if you correct for extinction. It is more than 500 parsecs away, which means that there's some interstellar extinction. This is bad because when we make a model, it will be strongly covariant with the temperature. But maybe since we know that the star is very similar to Sirius and the extinction is small, maybe we can work our way around that. In fact, the cis spectrum of this source is very, very similar to that of Sirius, except for the reddening part. It has no detected infrared excess. It has no known companion. And we have some spectroscopic and photometric observations by JBST, but only at the longer wavelengths of, say, NIRCam and NIRIS, because it's too bright at the shorter wavelengths. But nevertheless, this is a possibility to try and improve our system. We've got some observations, but we have to then try to figure out what they all mean, compare them to models, and do a lot of work on that. We could probably improve our photometric system, at least in the longer wavelength part of our coverage. If we can't do that, then there's also these faint DA white dwarf stars that we've heard a bit about and we'll hear more about in the next couple of days. These very nice papers like Axelrod et al. 2023, where we have these fainter DA white dwarf standards, proposed standards. They have lots of lots of HST observations because the HST calibration people were heavily involved in the project. And some of them, at least, are faint enough to observe in all our filters for NIRIS and NIRCam. And therefore, this is a viable alternative for something we can actually observe and tie into our magnitude system and check and so on properly. The thing here is that there's no history of using these stars as infrared calibrators at these wavelengths. So we don't really know whether the filter, the stellar models will accurately extrapolate to these wavelengths, but this is now something we can check out explicitly. And so the hope is, starting in calibration cycle 3, we're getting some observations of some of these stars, that we will be able to tie them in and make our magnitude system based on some combination of these stars and, say, BD plus 61753. And so this is going to be something we'll see about in the next few years. Whatever it is, it's going to be somewhat different than what we've done in the past, but hopefully we can get everything tied together in a really nice fashion. And that's the end of my talk.
Okay, are there questions or rebuttals? There must be a Vega lover out there.
Have I confused people so much that no one knows what to say?
Oh. Questions? Yes.
Did you say what the magnitudes of these are, or the range of magnitudes?
A number of them around 30th to 50th magnitude in, now the question is, I can't remember which filter I was looking at for that, but say around in, say, K band, yeah.
They are 17.5 to 9 eV.
Yeah, but anyway, some of them are too bright for our instruments, but some subset, maybe a third of them, are easily observable with NIRCam and NIRIS.
Yeah, to repeat, I think the reason Kevin's wish for an unreddened, really faint star is unreddened is going to really be hard. And the reddening law that you choose at the level we're talking about is not a trivial choice. So I think this is actually a very tough job to get a faint star that is a good calibrator once you've taken account of reddening. Carl.
I can't resist the reddening part. You're right that over a narrow wavelength range, the effective temperature and the reddening is degenerate. If you have a broad enough wavelength range, you can break that degeneracy. And that's one of the benefits of using Hubble plus data, is that we can break this degeneracy pretty robustly.
Yes.
And that's just because dust extinction and stellar temperature are different over a broad enough wavelength range. So I had an actual question for you. So you talk about you really want to have something we observe to set the magnitude system. Can you go into how we would use the observations to set the magnitude system that would be different from what we're doing with our Sirius Vega thing?
Well, it's not so much that you're setting the magnitude system with that, because you could do the same process with any model that you chose in principle. It's trying to understand whether it's consistent with all the other calibration we have with different photometric standards, how we get our magnitudes out. And if there were some small systematics there, we wouldn't be able to tell just from the simulations. We need to go to actual observations, because the simulations are wonderful as long as our knowledge about throughput is correct. But if there were some small problems there that would cause some systematics in our simulations here that we wouldn't be able to detect.
Yeah, in the case of G31, Charles Prophet supplied a prism spectrum with near spec, and given we had a spectral type, one could assume the temperature was more or less right. And then with the help of that spectrum, it was actually possible to distinguish different reddening laws. So that's another route to go, but we're going to have to use ancillary information.
Stop using the word law. We can break that one. It's not a law, it's a relationship.
It's laws.
Relationship with dust, Carl?
It's been very good.
Multiple laws, like 100 of them.
No.
Okay, any more questions or comments?
Thank you, Kevin.
Okay, next we have Peter Krebson. And we've already heard about your topic, so it's the Landau mission. So take it away.
Thank you. Testing 1, 2, 3. So yeah, how many of you have heard of the Landau mission before? A decent number, actually. Great. Well, welcome and thank you for having me here at this workshop. And I am new to this community, and so is the mission. And so this is a chance for us to introduce this mission to all of you. It is named with the permission of his spouse after the Landau, after Arlo. And so you might be hearing the word Landau used in a way you haven't heard it used before, and that can be a little bit confusing at first, but seemed to work okay for the Hubble Space Telescope. So the Landau mission starts with a team. I'm the PI. And our deputy PI, Elliot Perez, is here. In fact, we have a large number of people from the mission team here in the audience, if you could raise your hands. And a decent number of them are giving talks at this meeting as well. And I encourage you to seek us out during the breaks for future questions after today. Let's start my timer so I can keep track of it, but there it's going there too. And we have a number of, I think, 14 institutions participating in this, as well as a large number of students shown here, and potentially in the future, you. And one of the goals of my talk here is to excite you about this mission and encourage you to join us. So what is Landau? It is the 6th and newest NASA Astrophysics Pioneers Program selection. If you haven't heard of this program before, it's a $20 million cost cap class of missions in astrophysics, specifically aimed towards trying novel, creative approaches to old science problems and doing it quickly and cheaply, which didn't work so well during the Daniel Golden era of NASA, but we're trying it again. And the secondary goal of the Pioneers program is to train the next generation of space scientists and space engineers going forward. So we proposed in late 2021, early 2022, and again in early 2023. We received news of our selection at the end of February of this year. And as of 3 weeks ago today, we started officially. So we're brand new. Thank you. This is going to be the first Pioneers mission looking at absolute flux calibration. And we're going fast, and we got a lot to do. We're also one of the first of a modern approach to a hybrid mission architecture, utilizing both a space-based asset, in this case a 12U small satellite, and ground-based assets, and hopefully one of many in the future to come. And as proposed, the primary payload as we'll talk about later in more detail, but essentially shining a set of NIST traceable flux calibrated lasers down at ground-based observatories for deriving 0-point corrections, which we've heard a lot about this week, particularly in the visible and near infrared. So our notional orbit is a geo orbit, and I say geo specifically because I'm not implying geosynchronous or geostationary, and those are different. But geostationary is the one that stays in the same part of the sky. The geostationary refers to the orbital period, but there's ranges of inclinations, eccentricities, slightly below geo, slightly above geo. So there's a family of orbits that are possible that we're considering, but we'd like to have something essentially placed above North and South America for us to look at. So how did I come to be before you today with this idea and this mission that we proposed? Because I am not a supernova cosmologist, and I'm an exoplanet astronomer. And I was, back in 2017, was marveling, as heard from many during this week, at the knowledge gap we have between precision and accuracy, where with space-based telescopes, I can point at a star and say, it's changing by 10 parts per million. But I point at that same star, as you know, and ask how many photons per second are coming from it. And depending on who you ask, you get different answers, but on the order of 1%. That's a 3 order of magnitude knowledge gap. So I was thinking about all the interesting things you could do in exoplanet science with that. And so we started pursuing this topic about 7 years ago, and eventually led to where we are today. So it's an independent, it's a complementary and new approach to doing absolute flux calibration. In particular, we're taking an SI traceable approach, basically connecting your sensor counts to photons per second, or whatever your favorite physical units are. And you can see Joe Rice's and Daniel Koister's talks tomorrow, specifically discussing SI traceability. It's also timely. With the launch of Roman upcoming, Rubin being commissioned as we speak, and many other space and ground-based projects, as we've been hearing about at this conference, that are going to rely on accurate flux calibration. And I think we're also here today to work on this mission because it's just an amazing cross-cutting science cases. And so if you're familiar with supernova cosmology, I've had to learn about some of these dark energy constants that I didn't know very much about before. So I encourage you here to also learn a little bit about some of the other science cases that this will also apply to, including exoplanet science and stellar astrophysics. Now, you might already be familiar with standard stars, obviously, but maybe not know some of the really exciting things you can do with improved knowledge of stellar radii, for example. And so Jamie Tyre and Dan Stevens tomorrow are going to be talking about some of those science cases, and Angel Tanner has a poster that's been available today talking about some of the exoplanet science cases. So we're already familiar with the supernova cosmology case. And if you say look at the CalSpec model spectra for GD71, pre and post 2020, and look at the visible to near infrared absolute flux ratio, it deviates by more than, say, the Roman Space Telescope requirement. And our aim is to have a level 1 requirement of 0.5% absolute flux calibration, not color, but flux in each of the wavelengths we'll be operating at. To touch a little bit on the exoplanet and stellar astrophysics science cases, this is although it sounds like exoplanets is consuming the rest of astronomy these days, this is a mass radius diagram of exoplanets roughly between 1 and 10 times the mass of the Earth. And you can see these error bars essentially cloud our view of the evolution of exoplanets and the formation of them. We know there's something called the Fulton Gap that separates Neptune's and terrestrial worlds in our universe, but understanding how wide and how deep that gap is currently limited by our understanding and accuracy of the radii of transiting exoplanets, and we really want to increase and improve those measurements. And thanks to Gaia, as we heard all the way back on Monday from Chris Stubbs' talk, it's no longer our uncertainty in the distances. On the stellar side of things, I'm really excited about the possibility of being able to assign stellar ages to anything older than a gigayear, right? Which previously has been incredibly challenging to do. So to talk now more about the mission itself, we are a hybrid mission architecture, as I mentioned earlier, and that's to take advantage of keeping the cost and most of the complexity on the ground. But of course, there's a trade there that we then have to also deal with the Earth's atmosphere and the transmission challenges associated with that, but allowed us to fit into the Pioneer's cost cap. And in terms of orbit, I mentioned the GEO orbit in particular. Relative to LEO, it has a much slower angular drift rate, so it's possible for ground-based telescopes to more easily track the satellite. And we'll talk a little bit about some of the observing modes we're planning for that, while still preserving umbral crossings through the Earth's shadow, so you can essentially turn off solar reflections. Of course, there'll still be terrestrial and lunar reflections as well. As proposed, we had 4 mission ground stations to achieve our proposed science traceability matrix science objectives. Ruben is, we have Brian Stalder on our team, who's the commissioning camera scientist, and he couldn't make it here today. He's very busy in Chile right now. We have the SNFS spectrometer, integral field spectrometer on the 2.2 meter, which Daniel will talk about tomorrow, as well as my university's campus telescope, because I can. And then to have, so we have a near-infrared camera as well. One advantage of doing that is we get a bigger field of view with the near-infrared camera as a result of having a smaller aperture, given the F number. And then also the near-infrared camera on work on Palomar. For the payload, we're drawing upon heritage both intellectually and specifically from both OrcaSat, which flew in 2023. Justin Albert, he's here, and was a pathfinding experiment in this regard. It did launch from the ISS in January and then deorbited due to increased atmospheric drag in August of 2023 in Leo. It was challenging to observe it, but really interesting pathfinder. And then Candle, the PI is Susanna Duesta, and she's here as well and on the SOC for this conference. And Candle has been working for the past year with designing a 3 component, well, 3 to 4 component, 3 illumination sources plus an element wheel of sensors, 3 component payload, 1 a set of laser modules, which was what we baselined in the Landalt proposal, and I'll show more detail about in the next slide, as well as a solar reflector. So that would allow you then to map the individual laser wavelengths to the rest of the spectrum, and a monochromator if you'd like to have essentially a tunable wavelength device on board. So this is trying to build our ideal calibration source. As proposed, the Landalt payload primarily just focused on this laser module with a set of 4 to 7 lasers. And one of the key innovations in the Landalt mission proposal was using single mode fibers instead of, say, an integrating sphere. That allowed us to move the satellite further away than Leo, but while still maintaining a really well-known near Gaussian spatial beam profile, which then drives our spacecraft pointing requirements and are readily achievable. So no collimating optics, which would be nice. It would deliver more power, but that would come at the expense of losing knowledge of your far field beam profile. So it's kind of the geo orbit and the single mode fibers and the power we can achieve all kind of balanced out to work for roughly 100 milliwatt lasers in these compact butterfly packages. And we would build these, and we're going to be building these at George Mason, and then taking them nearby to NIST here in Maryland to characterize them. And we've chosen wavelengths, and I didn't list the specific wavelengths here on purpose, but we've chosen the wavelengths to overlap Roman, Rubin, and near-infrared band passes, balanced against some of the technological hurdles, right? We need to have lasers that are space qualified and readily available in these compact packages at powers that would work for us. So we've simulated what Landalt would look like. And so this is a simulated image of Landalt while tracking at a sidereal rate, and we see it blinking on and off with a ½ second on, 1.5 second off modulation. And the blue lines there show that satellite blinking on. This is an R-band 90-second exposure with a 0.8 meter telescope. So you don't need a huge telescope to see this. And you can see it in comparison there to a 13th magnitude R-band exoplanet host star in this particular case. And this was with a 785 nanometer, 100 milliwatt laser. So it's drifting along at 15 arc seconds per second, essentially stationary in the sky, but of course the Earth is rotating. So we started thinking about how are we going to get accurate photometry from all of this, and we came up with some novel observing modes. I've got just a couple minutes left. Mode 1 is the standard mode that you just saw. We sidereal track with our telescope and we see the satellite streak by. Mode 2, which people often use for measuring light curves of, say, asteroids, you track the asteroid and let the stars streak by. Or you can alternate between modes 1 and 2 in an ABBA pattern, which is mode 4 on the right. And that has some advantages and disadvantages. The advantages are, well, in A mode, the stars are point sources. In B mode, the satellite or asteroids in a point source, but everything else is streaking. So you still have to deal with temporal changes or aperture corrections. So we came up with mode 3 shown here, which is a half sidereal rate tracking mode, if you think of GEO, where the stars and satellites streak equal and opposite amounts, so that you can, provided you get the tracking rates accurate enough, you can eliminate the aperture correction in deriving your photometry, because they'll be identical PSFs in theory. And so we've been testing this as part of where we're at in the mission right now with existing GEO satellites. So will you be able to participate? Let's say you have a telescope back at home. Yes. This satellite is going to be relatively observable with relatively small telescopes. We're planning a guest observer program. We've been developing tools to assist in that. Turns out not entirely trivial for astronomers how to think in non-sidereal modes from the ground. And here's our timeline. So we are currently in phase A as of 3 weeks ago. We were pre-phase A before that. So on this timeline, we are here in Q1 fiscal year 2025 of the federal government. So for the next 9 months, we are doing design studies and trade studies. We're looking at things like finalizing the design for our payload, looking at different options for our orbits, addressing various challenges that we've identified since we submitted the proposal. And then we'll have a critical gate review between 6 and 12 months from now, where we will have a system requirements review and mission design review. We pass that, then we get to start moving on with standard mission phases, preliminary design review, critical design review, integration and test, with launch no earlier than late 2028. So I'm going to put up my concluding slides here. We just started. We're in phase A. We're conducting these trade studies and refining mission designs. We want to hear from you. You probably haven't seen a paper about this yet because it hasn't been published. There's just one little abstract, AAS abstract. And so we are working on a paper to tell you more details about this mission. And we want to have you scan this QR code and join us. With $20 million, we're going to need a lot of community support to carry out our science objectives. For example, taking some of our measurements and extending them to various other observatories and catalogs. And so you can scan this QR code, or we'll post it in the Slack and sign up for our interest groups. And thank you very much, and I'll take questions.
Okay, thank you, Peter. Questions, comments? Okay, we'll start up close.
That was a really cool idea, Peter. For the spacecraft, do you have to worry about scattered light impacting the signal from your lasers?
Yes, absolutely. So you do have to worry about the sunlight reflecting off the spacecraft. So that's why I mentioned umbral crossings that will turn off solar reflections. So for example, for a satellite in a geosynchronous orbit, you will get 1 hour umbral crossings every night for roughly 12 weeks out of the year. And our primary mission is roughly 1 year long. If you choose different inclinations, you can actually change that to up to every night for the entire year to get those umbral crossings. We are actually at this moment looking at a clone of our satellite bus currently in geo orbit. And we actually haven't been able to see it yet with our 1 meter telescope with 122nd exposures and broadband R. So it does not reflect a lot of light. It's not like those giant GPS and communication satellites that are very easy to see out in geo. So the geo also helps us with solar reflections too.
Okay, Chris Stubbs has a question.
So this is great. You can broadcast all those wavelengths simultaneously?
So our payload, notional payload design as proposed would be alternating between different lasers. They're roughly 100 milliwatt lasers each. And our spacecraft bus power is 40-ish watts. So there's a possibility we could explore modes where we have multiple lasers on simultaneously, but we're trying to follow the KISS principle of keeping it simple for now. But if you have good arguments why we need to be able to do that, then I'm happy to hear them.
You need to be able to do that.
Okay.
I would just add,
From Thomas Dutkovitz.
please, just close. I would just add that the spacecraft and the payload as designed is aimed to meet the requirement of operating all of them, but the baseline requirement is to operate some of them in real time.
Yeah, there's baseline and threshold requirements. So we have our kind of, we want to say we're going to do this bare minimum, but of course we'd like to be able to do more than that.
Hi, great talk. This is really exciting. You mentioned, operating in these bands to support some of the latest and greatest space-based missions, but I'm curious, are you planning in your general observer program to be able to actually point at a space-based mission to help with calibration or no?
Yes, and so we actually just looked in that question very recently. Surprisingly enough, Hubble could look at us. We did the math, and it turns out it's actually anywhere from half a sidereal rate to twice sidereal that Hubble would have to track. And likewise, any other LEO satellite like SphereX or others could look at us. Unfortunately, Roman or Webb would not be able to look at us because we're too close to the Earth, but maybe we could look at something that they could look at the same time.
And I personally tracked geosync satellites with a rather crude ground-based telescope, and it can be done quite trivially from the ground if you're ready to do it. Okay, more questions. Okay, I think, way back there we have a question to finish.
Hi, Gerard Van Bell from Lowell. What's the ground footprint of the single mode fibers?
Great question. So we're choosing single mode fibers, which numerical apertures are typically around 0.1, which is a beam opening angle of around 7 degrees, which at the Earth's surface is around 1,200 kilometers wide. Kind of full width half max kind of number. So we could illuminate all of Mauna Kea or illuminate all of Arizona and California, and we'd have beam knowledge, and it would be to our advantage to have multiple telescopes looking at the same time. The hard part, as many ground-based observers know, is coordinating multiple observing facilities, especially scheduled ones that are classically scheduled.
Okay, let's thank Peter again. So our next talk is from Kristen Madsen about the International Astronomical Consortium of High Energy Calibration Method and Activity. That's rival for the longest title we've got.
Oh, it is very long. I agree with that. So you might wonder who I am. I wonder who I am too many times. But and I am an imposter in your community here because I am that solar X-ray flare that came through the solar shield. I am your X-ray equivalent, the X-ray calibration equivalent. And so I'm Kristen Madsen, chair of the IACHEC. So the IACHEC is the International Astrophysical Consortium of High Energy Calibration. Every time I have to say that, I have to think really hard. So this is a lighter talk. I'm not going to try and tell you how we do our cross-calibration in X-rays. What I'm going to try and help you here is I'm going to tell you how we have organized ourselves with cross-calibration, which might be useful for you because this has been going on for a long time. So are we there? Almost?
Oh, you're good.
Okay. Right, and it's interesting because I went outside and I looked at your sign-up sheets out there. And unless, I don't know if you know that, but the sign-up sheet out there for the discussions that is the longest is the cross-calibration one between surveys and instruments. So, and that's really what the IACHEC is about, is the cross-calibration. And, oops, where's the forward button? There's the forward button. It was founded in 2006. And you don't know who these names are, you don't know who these people are. the reason it was founded in 2006 is that in 1999, the two big X-ray flagships, which are still around, were launched. So there was the one from ESA, which is XMM Newton. There's the one from the US, which is Chandra. At this time, about 2004, 2006, you started having the community do science, and they would do science from both instruments, and they'd combine these data, and they'd see big problems. And of course, they'd approach each of the instrument teams and complain about, well, you're not seeing the same as Chandra, and the other people would say, well, you're not seeing the same as XMM. So the instrument teams from XMM and Chandra said, okay, let's go to Iceland, very isolated, sit down and talk about this. And this happened in 2006. Since then, we have actually had a meeting every single year since 2006, except during the pandemic. And what really happens at this meeting is that we have 4 days, and we do exactly what you've been doing here. We present our different calibration, but in addition to that, we actually do work. We have sit-downs, we pull out our laptops, we look at the data, and we say, okay, what are the problems we are having, and how do we solve it, and how do we tell the community about it? And so we actually do work. And since then, it has evolved that we between these meetings, which is once a year, we have these working groups, and we try to keep up the work that we do that 1 week a year where we are very active. We try and keep up that a little bit through the rest of the year. And the other thing that we do, it's the international. So we do shift between countries. We try to do US, Europe, Asia. So we did Spain this year, and we're going to do Japan next year, and then we're going to go back to the US. So we try to go around because very often you don't have enough funding to get to different countries, so we try to go where people are. So the IACHEC has then since evolved, and the primary purpose was we wanted a forum where people can come and they can air their dirty laundry and their weird questions without being judged, and everyone looking at it and say, well, that's weird. Well, we see the same thing. But in addition to that, we've tried to make it more formal so that we all sit down and agree upon defining the calibration standards. We do documentation, we publish these things, because the worst thing that happens is if you don't tell your community about the differences, they're going to make up reasons for it, and they're going to try and do their own calibration that they're not qualified to do. So we try to inform them about the differences and what we as experts deem the reasons for it. And then, to improve cross-calibration across the different missions. Whoops. So just to show, those of you who are not X-ray physicists, there are a couple undercover ones here. This is what a spectrum looks like. We are no longer in wavelength, we are in energy. So it's typically from 0.1 kV up to 100 kV. This is just an example. So this is X-ray sources, they vary all the time. We do not have a Vega, we do not have a Sirius, because they're doing things all the time. This is our most boring source, which is 3C273. It's the first quasar discovered. And it is flat, featureless. It is a power law. However, it changes by up to 40% depending on a couple of months, the flux of it. So it's not a steady source in that, but if we all look at it at the same time, it is fairly well, in those 50 kiloseconds we look at it, it is well behaved. So here's an example of these 5 observatories looking at it at the same time, and these are sort of the differences that you see when you do that. And so that was just 5 observatories. There are many more X-ray observatories that are part of IACHEC. Here's just an example, and this is, so there are now 2 Chinese ones, which you see there, HXMT, the Einstein probe, they were just launched. There's India's Astrosat, then we have got Integral, we've got Fermi, we've got CRISM, which is from JAXA, XP, which is here in NASA, that's a polarimeter mission, and NISA, which is on the space station. So there's very, very many different varieties of X-rays. They're all specialized in one specific field, but they're all part of the IACHEC, and we all need to cross-calibrate because X-ray physicists love to combine data from different instruments, and they get confused when they don't get the same result, when they don't agree. So just a little bit about what are the things that we care about in X-rays. So we are not as obsessed about, sorry, not upset, maybe I should say upset. Absolute calibration isn't such a big issue for the physics that occurs in X-rays. When there is cross-normalization, when there's offsets between instruments, it doesn't impact our science as much because the science happens very close to the engine, and so distance quite often doesn't play into this. The physics of what happens when it accretes, when it does outbursts, isn't as impacted about the absolute calibration. What we really care about is slope differences between observatories. Because when you combine two instruments and the slopes do this, people make up reasons that are usually wrong. And they always, which one is right? So depending on which observatory they love best, they say, oh, that one's right, the other one's wrong. But the reality is, none of us are right, because in X-rays, there's no absolute calibration. It is really driven by our instruments themselves. So the instrument that from the ground is the best calibrated is the one that we tend to trust the most and say, okay, well, that was really well ground calibrated. So in terms of absolute calibration, that one's probably more right. But in reality, we don't know who's right and who's wrong. So the bulk of the IRCheck effort is really the slope differences. And that's what we tell the community so that they know what to expect. So if they see differences, that they know that that is an instrument thing. Don't worry about it. Physics didn't break. And the cross-normalizations constants, they're really just a bookkeeping exercise because you have instruments that say we will not change our absolute calibration unless we can justify that our ground calibration was wrong. So you can't have people just changing their calibration based on what we see. Okay, so IRCheck has these working groups. There are quite a bit, and they're organized in between methods. You know, what do we do with backgrounds? How do we fit backgrounds? Backgrounds is a big thing in X-ray. What are the detector physics that we need to care about? Coordinated observations, mission lines, calibration statistics, timing, and then we have specifics. We do have a couple of standard sources, but they're not standard the way yours are. Clusters of galaxies tend to be well behaved. The problem is they're extended. That gives us problems. Non-thermal supernova remnants are pretty good standards too, but they do vary as well, and they're also extended, and they're bright. Thermal supernova remnants, they're better, but they're also extended. And then we have some infrastructure, which is like heritage. How do we keep this knowledge base and keep it for the future? I'm going to skip this slide, but basically what it is what I've mentioned is we need to tell the community what's going on, and that's really so that they don't draw wrong conclusions and try and do their own calibration. So the responsibilities are really to define new calibration standards in X-rays. We look at sources and see, is this a good source for it? And then to compare results from different missions. And here's just some example, 3C273, as I mentioned over there, you can see the differences. You can see how these are normalized to one spectrum, and you can see that there are significant differences between these couple of instruments you have there. And the same thing with supernova remnants, a thermal one where we have the lines. You cannot really read what's down there, but the numbers down there, that's different instruments and how different they see where the position is, the position of the different lines is. So we track that so that people know what to expect. Then we review in-flight calibration plans and results from future missions that are about to launch. And CRISM, which is the JAXA mission from Japan, recently launched, and we were very involved in reviewing. They look what has been done in the past and what are they going to do. So we do a lot of that. And also propose new things and inform on the calibration updates. And this is the one thing where, so the cluster temperatures is the one thing that really drove this because it has cosmological implications, these cluster. And that was the one that drove because we have very big differences between Chandra and XMM. And since 2006, this has been ongoing to try to fix this problem. And we still have not completely understood why these two instruments give different values of the thermal temperature. Oops. Okay. then we, so that was advise new calibration plans for new missions and support some, so do some definitions of what should, so we have published, for example, here we've published in-flight calibration, what to expect, which sources to use for which type of calibration. If you do want to do PSF calibration, if you want to do gain calibration, these sort of things. And then the iCheck has been, for the last decade, involved in pretty much every single instrument that has launched since then, which is 1, 2, 3, 4, 5, 6, 7, 8 instruments. Okay, and then let me see. This thing is dying, I think. Here we go. So best practices also, because statistics in particular are very important when you do X-ray analysis. And so we've come up with different guidelines for people for how to do the analysis, X-ray analysis in the proper way and to do it with the proper statistical analysis. The other things that we are trying to do, because I mentioned that we really don't know who's right. We don't know which instrument has the correct absolute flux. So we've come up with this concordance project, which is a very, it's in collaboration with statistics, with a lot of statistics people. There's 3 papers that have been, that's been published on this. And what we try to do here, I admit, I do not completely understand this method myself, but really what it boils down to is that we have all these different observatories that have different effective areas and that come up with different results. And if you take all of them together, you should be able to figure out which one is the actual truth. And so that's what this concordance project is. The statistics people tell us that we can do this. So we are working on that. And you do that with very many different sources, and then you see which result you come up with. And then the question is, once we've done that, if we really come up with an answer, is then we have to work on how to adjust the responses of the different the response files of the different observatories. But that is another issue we'll have to deal with. So the other thing that the iCheck does, which is very important, is X-ray sources, as I said, they're only the same when you look at it at the same time. Otherwise, they're different. If you are a week apart, you cannot trust that it did not do something in between when you looked away. So what we do is we help the different missions, and this is internationally, different missions. We do cross-calibration campaigns. We organize those. We help. When a new mission launches like CRISM, we all get in behind it and we coordinate with them that we observe different targets together with them so that they have references for their calibrations. So, and we do this in yearly. We have one yearly campaign, which is between the crab. So the crab is it's very bright in X-rays, but it is quite stable on a long-term scale. It does vary by 3%. So the hard X-ray instruments, they use the crab to look at on a yearly basis. So we do that. And then there's 3C273, or boring, very boring, standard source, which we do a yearly campaign as well. And for that, every single observatory looks at it at the same time. And this is if you think about the amount of money that goes into that campaign, it's quite a lot. But we've been doing it every year, and we have up to like 10 years of yearly campaigns on that. And with that, I wanna summarize that iCheck has really brought the X-ray community together, and most importantly, all the calibration folks on the different missions, and enabled us to talk together in a way that we probably wouldn't have before. So we can sit down and we can pick up the phone and say, oh, there's something weird going on, and have very informal discussions. And we continue to do that on a yearly basis. And we continue helping new missions, especially the Chinese missions have benefited incredibly from this. And we've been very lucky, too, that they have chosen to be a part of us. And so with that, I hope I have inspired you to how you might want to shape your own community going forward. So with that, I'll thank you.
So before we get to questions from the audience, I have a couple. So I'm acquainted with the effort with Chandra at Marshall to have this long tube and try to calibrate it.
XOCF.
I think that was not entirely successful. I thought, on the other hand, that calibrating your detectors could be done quite accurately. And so the problem in that experiment was you didn't get to the far field, and in general, this must be an optics problem. Is that correct?
So I would say, so in the book, Chandra is probably the most well-calibrated instrument. So they had the XOCF, which is at Marshall. It is a 500-meter beam line. So we illuminate the X-ray optics with that to quantify what's the effective area, what is the vignetting function. The problem with doing it on the ground is that you have a divergent beam. You do not have a source at infinite. So when you look at it there and between looking on the ground and then projecting what happens in space, you need a ray trace. And so something can happen in between there. So the instrument, we think the calibration of Chandra is probably the best one, and detectors as well, but there is gain evolutions when they come up there, gain shifts and drifts and all that sort of thing.
Okay, so this is mostly an optics problem and a little bit of an electronics problem.
Yeah.
Okay, so with that, questions? Okay. Oh, no, you always ask. Save you. Let you go.
Yeah, thanks for your talk. It's great. I don't know the X-ray people at NIST, but there are people like this at NIST. And my question is there international standards labs involvement in any of this calibration work?
Yes,
Okay.
very much. So we have the calorimeters are flying now, and NIST is very much involved in so CRISM, which launched last year from JAXA, was calibrated with the EBIT from NIST, provided by NIST, I believe. Yes, so NIST is involved in that. There's this whole atomic database effort too, atomic lines and all of that. That now that we have a calorimeter, we're going to, before we didn't need to, we had spherical cows, but now we have a calorimeter. Now we need to really understand the atomic databases in X-rays.
Yeah, I mean, just to underline the problems that Kristen was talking about, sources, two of your main sources are well-known blazars, 273 and 2155.
PKs, yeah, 2155.
They're both highly variable sources, but they're point-like, right?
They're flat and point-like. We want featureless and point-like.
Exactly. So that just explains why you're in a tight corner in terms of picking calibration sources. More questions?
Thanks. That was excellent. Fantastic talk. So, has it ever been considered to do for a potential on-orbit calibration? Maybe absolute slope might be the nicest thing to be able to calibrate on orbit.
Yeah.
It is maybe sort of a combination of the Marshall source, which of course you can't. It's way too big to put into space, but just the source of the electrons, just the electron gun, basically, could, and as the target for the electrons to create the X-rays, have something like the MSX mission had, with shooting out some.
There was a mission that was proposed or was in development at Goddard, kind of like Landolt, which was called CalX. And Goddard wouldn't support it, so it fell out of so it wasn't proposed. So things of that we are thinking of that. It's just getting through the centers and being compelling and knowing enough. Yeah.
Hey, back here. Come on. This seems like a very healthy organization. Can you say a little bit about the funding? Clearly, you must be successful in.
Zero funding. This is all community motivated and, well, indirectly funded by each of the mission's calibration teams. So it is the meetings themselves. We don't get, well, we sometimes get a little bit of funding from the different missions, but all the work that goes there is really community driven And it is the time that they need to spend on their missions that they then also spend talking about cross calibration. So in that way, but there's no specific funding. We have attempted to do APROS for a specific question like this 3C273 data, where we have 12 years of it to get a person to do that. That's our only way to get funding, direct funding for that.
But all of the members of the organization must be doing a good job convincing their local institutions of the necessity of this, such that you all can continue to get your local funding.
They do.
Yep, great.
And it's operating missions, right? And it's the iCheck it's very much the same. We've been there for a long time. Our problem is to get new input. But it's pretty much driven by people who've been there for a long time, know each other very well, know their institutions very well.
So Greg is signaling there's a question over there.
Maybe you can talk about something I've seen in other fields is that they let the cat guard the cheese. So do you have any external mechanisms that allow that the people who enjoy the data and publish it and want something to be something to kind of balance the power between we do the science to this is an external unbiased system that could help us as a community find the right answer?
So I think what you're asking is if there is a specific problem that the community sees and they ask us, can you fix this problem? Is that a driving motivation for us to? No.
It's very clear we all want something to be small or big or whatever the answer we want it to be. That's our community. Typically, when you do this in like an unbiased manner, there's an external mechanism that does it for us. It's an arbitrary. So is that something your community thought about, or just the community came to an agreement what the right number is?
So you mean in terms of the cross calibration?
As an example.
Numbers. So it is as a community, but we do not. So this is why I keep saying we don't know who's right. We do not say everyone should believe in Chandra, everyone should believe in Nustar. We say, okay, we understand why they're different. This is why they're different. So when you as a scientist see these differences, you can go there. You cannot conclude that one is right, one is wrong, but you know why they're different. So we're very careful about not saying, although we had a ping pong tournament and Swift won, which is one mission, and the prize was that we should all recalibrate to Swift, and we were like, no.
One more question. Florian Kerber from the European Southern Observatory. Thank you very much. You pointed out that you hope that we could learn from you, and you have witnessed our discussion about cross-calibration. And so, aside from that, nobody is right. What is your, let's say, secrecy, like your little secret for success? I mean, what helps you? What kind of mindset really makes it click?
I think it's important, and this is, again, focusing on who is right, I think is the wrong thing to do. I think figuring out why you're different and getting that out to people so that they understand that is what made us at least successful. Because as soon as you get into who's right, who's wrong, people get defensive and they get argumentative. And that can be dangerous and counterproductive. So instead of saying, okay, we understand your effective area, it looks like this, ours looks like this, that's the result of it. That's, at least for the x-rays, that's what worked for us. Otherwise, everyone would stomp off in a huff and be like, why did I say we were wrong because clearly they don't understand this.
So I can't resist the comment, but from your pictures, it looks like you have a meeting once a year that's almost like this meeting on scale, and the difference is people work. Oh, with that, let's get Okay, I think we're done with the session, and let's see, do you have an announcement?
Yes, we have a discussion session. We don't have much time left before the FDAS-B, which is the next event. So I invite here Stefano Casertano from the Raman Telescope branch, and where is Susanna? Was she? and Susanna from NIST to moderate the discussion about the Raman spatial calibration and tell you a few. Okay.
I have a question for Kristen, actually. Are there commonalities? I mean, you use detectors that have some resemblance to the detectors we talk about. Are there commonalities in the problems you face, like degradation of detectors exposed to radiation and so on, that might result in some useful connections?
Yeah, definitely. I mean, we see contamination issues. A perfect example is Chandra. Chandra keeps losing, they have contamination building up on top of its detector, and it's now 10 times as thick as the filter. And at this point, they cannot heat it up because it's just going to fall back down on it again. So there's contamination issues. There's also harder X-ray detectors just from radiation damage. You see gain shifts from that. So certainly, yeah.
Okay.
There's optics too. You probably have more of a obscuration problem on.
Let's keep this going after. Okay, thank you.
So we're trying to figure out what to say. So I will just start by saying that Stefano and I have worked for some time on Roman calibration. We wrote some of the calibration document things way back when. And as you all know, Roman is the next big 2.4 meter telescope doing awesome science. My microphone is on. Mine is on. Anyway, so we thought we would open it up. You know, you've heard a lot about calibration. We've heard a lot about Roman. We've heard about James Webb. And so I think this is an opportunity for y'all to ask questions and engage in a discussion with what we can do calibration-wise, or what will be happening calibration-wise. No, I don't think Roman will be observing Vega either. So we'll just put that one to rest.
Yeah, just to, can you hear me, I guess?
Yeah.
Yeah, just to set the stage a little bit, I think there are, I mean, Roman obviously has, being a survey mission, in part at least, has very, very strict requirements on calibration. We really need to get things right. It's not enough to say we want to agree, we also need to get them right. And to a fairly high degree of precision, 0.3 to 0.5% are the numbers you will see in different areas. And there are two sides to that. One is the absolute flux calibration and color calibration, which is what most of this meeting has been about. The other is converting that, you know, from your standards to actual observations. So correcting all of your observations to the right calibration, which can mean, you know, correcting for any color variations, correcting for flat fields. You heard us talk about from Eric Schweitzer this morning, and all nonlinearity effects, all kinds of things. So those are both important, and they both need to work right if we want to achieve, you know, the goals of Roman. So I didn't mean to be to damp everybody's enthusiasm in this, but but it is a lot of it is a challenge and it's a lot of work.
Go.
Battery efficient and breathe.
So I'm Joe Rice from NIST. I didn't hear hardly anything, maybe I missed it, about persistence effects in the Mercadtel detectors, which I know are a big problem with Roman, but I would assume they're a big problem in JWST as well. But I mean, is it not a big problem? Are they all kind of being corrected okay? Or what's up with that?
So I can say a few words about what the current plan is, which may change.
For Roman.
For Roman, yes. But I don't know if you want to say something about JWST first, or?
I think he just meant that we know that persistence is a problem for Webb. So the question is, what is Roman going to do?
So the current estimate is that even for the most challenging observations, which are the galactic bulge time domain series observations, only a small fraction of pixels will be affected by measurable persistence at the level that matters for the data. And those will be flagged. There is not going to be a plan, or at least there is no plan for now, to correct for persistence. It's just to flag pixels affected by persistence and throw them away. The estimate is that the most will be 1% or 2% of the pixels. There are two reasons for that. Persistence for Roman is lower for those detectors than it was for the previous generation, the H2RGs. These H4RG10s are much lower persistence, and it decays fast. It essentially mostly gone from full well to after 10 minutes. Not entirely, not completely, so one has to track and one has to flag anything that's been affected by persistence, but at the level that has been tested in the lab, it appears to be, those are the numbers. We will check that during commissioning, obviously. If we find any surprises, that will be, we'll have to rethink. But that's the current status.
I saw Misha was raising his hand too. I was just going to say, as sort of the best precursor example, Euclid, Misha showed us some effects. I wonder if the Roman people sat down with the Euclid people and said, we won't have that problem. Here's why, basically try to red team the architecture. I know there's probably not a lot that can be done, but I just wonder if it has been done. So it may be less of a surprise and we could start planning for it.
So are you referring specifically to persistence? I wasn't here for...
Yeah, all the effects. So the X-ray shining through, scattered light, light getting through shutters, all this kind of thing that you showed us.
Well, we don't have any shutters, so that's... we do have a dark element. So, yeah, some of the effects that I've seen discussed for Euclid have to do also about how the data are sent to the ground. The data are mostly, as I understand it, mostly processed on board for the infrared camera, and the only rates are sent to the ground with some exceptions. And instead, for Roman, a large fraction of the data will be combined into groups, Jelly style. We call them resultants because they're not uniform, and then will be sent to the ground before processing. So that will probably help in some areas. In other areas, we certainly have to look very carefully at Euclid experience and learn.
Can I comment on that? Also, a couple of things, persistence and to start from the last issue you rose, we had a couple of months ago, we had a lessons learned exchange between Euclid and Roman, which I think was highly appreciated. And also we wanted to share that because a lot of headaches that some of them hopefully could be avoided. It's true, our readout modes are completely different, or not our readout modes, but what we can downlink to Earth is very different because we have a giant optical camera where we download all the pixels, and that limits, or that basically eats up 80–90% of our telemetry budget. So we can only do onboard processing, and we downlink the slopes and the bit flag, or a 8-bit flag, depending whether we do imaging or spectroscopy. So our for the near-infrared detectors, a couple of raw lines, so we can do better detector monitoring. About persistence, it's a huge headache. I'm glad I heard rumors that Roman hopefully or might not be suffer so much from that with the H4RGs, but for the H2RGs, it's an issue. We calibrated that a lot on ground. We took probably petabytes of data, or at least many terabytes. And we had a 2-week calibration campaign about persistence during performance verification. Then we had all the stray light issues and tracking and X-rays, and we didn't really get to actually regroup and look at that until very recently. And what we've seen is that the persistence models that the persistence data that we have, they work about for a month or 2 months, and then they start to don't really fit anymore. So we are updating our in-flight calibration plan right now to implement the monthly persistence calibration, which is not 2 weeks long. It's just 2 hours. It's a single flat field followed by a couple of darks, and then repeat that once more to get rid of some cosmics. And that should allow us to implement a reasonable persistence calibration. So far, we masked it, but because we have this constant changing of
3 images spectroscopy, you get a very complicated persistence pattern, also because we see it for hours, in some cases, probably 10 hours if the sources are really bright. And so we need to move away from masking towards more actual correction.
Ami Choi from Goddard. So I just wanted to actually mention what Misha just mentioned, which is that we had a series of lessons learned from Euclid, and we did indeed very much appreciate that. I think actually that lessons learned, there were also people from other groups like SphereX also had a representative there. They also have H2RGs. So yeah, that kind of thing is really important and sparked off a lot of really useful conversations, I think, just even on the Roman project side about, checking straight light paths and how are we going to make sure, we don't have the same kinds of issues. I think it's inevitable, as you mentioned, it is a little too late to actually, fix anything if we really found something. There hasn't been anything specific like that, but just conversations about what could happen. Talking about water, like ice contamination, things like that. So yeah, I think it was really great. And it came up in conversation at this meeting earlier that, it'd be nice to be able to share those kinds of things immediately at the level of where we actually can make a difference. I guess it's kind of hard, just given timelines of missions and such. But yeah, it was very useful. And I'll mention one other thing, which is that, so I'm also on the cosmology pit. So for weak lensing and galaxy clustering, we have a plan to every year have a review by some sort of review committee of our pipelines. And most recently, we had a face-to-face meeting about 2 weeks ago now, where we had a lot of people who were representing Euclid and other surveys. So, people who kind of have seen these pipelines from other, for other purposes. So, and I think a lot of the other project infrastructure teams do the same thing. So, yeah, hopefully we'll learn a lot of lessons that way too.
Okay, I have a question because you've got many, many detectors, right? And
18.
with
18.
Yeah, with NearCam, it's already a problem. But how are you going to cross-calibrate your detectors to the level that you want to do? So it's a really big job.
It is. We're sort of laughing because we were getting some of the results from the TVAC tests, and both Stefano and I are on the supernova pit, and this is exactly a question we started to address. We don't have a good answer yet,
but there are things that help. The fact that we are going to be observing a large fraction of the sky, many different orientations, many different overlaps, etc., is going to enable us to do comparison on a continuing basis. So you can really basically, you observe, and then you observe again, moving half the field of view or 3/4 field of view, whatever it is. Some of the sources will happen to be at different locations. You do that for a year, 2 years, you're going to have a lot of information.
yeah. So just to add.
But it doesn't mean it's easy.
So to add to what Stefano was saying, we've been discussing things like having reference fields that you can go back, that have hundreds of stars that you can then put on all the detectors in a lot at once, right? And then do sort of that type of an analysis. It would be lovely to be able to put your favorite white dwarf on every pixel, but then that would take up the entire mission time.
Isaac.
Okay, Rebecca Hounsell, UMBC, NASA Goddard. So with regards to white dwarfs, what is the current plan for like the number of white dwarfs, like the standard stars, the plan for doing that type of work right now for Roman? I know I'm kind of putting you on the spot here, but I wanted to start a discussion about it. Yeah.
Okay, so I'll give you a quick answer to that, is that we know that the 3 primary white dwarfs in the CalSpec system are a little too bright to be observed in the standard observing mode. They need special observing modes. And this has always been a challenge, even with HST, as you're observing your standards in a special mode that you're not always actually observing in. So I think now we have the community, if you will, through, for example, Avi sitting next to you and a bunch of other people who are looking at adding faint white dwarfs to CalSpec or just to make them available. So I think those are going to be probably at some point we'll have to figure this out, but those would be useful for the Roman.
Is that like
calibration.
5 or a lot more?
No, it's tens. It's tens. It's tens. But
I'll just add that the JVST Cycle 3 Cal program has several faint white dwarfs. I don't remember the exact number, 5-ish?
3 and 4.
5.
Just 3?
3 this
3,
year.
but 2 will be also in the next cycle, I think.
Right. So like 3
So
this
5.
time, we're going to add some more. They're not large numbers, but I mean, and the whole point is we're kind of building towards Roman.
And to add, Susanna's been too modest to mention this, but there are 3 white dwarfs in the Euclid Deep Field North and 3 in the Euclid Deep Field South. Those are also been observed have been observed with HST and will be observed with JWST, and they will also serve as additional standards. So I think we are putting together a stable, big enough, I'm not sure, but not too small.
it won't be 3.
That's my fear. 3 or
Yeah,
5
but
No. It's tens.
yeah, we need to think about that. Wi-Fi camera 3 infrared might be not available forever. And so if we need, for example, infrared GRISM observation from HST for a cross calibration HST, JWC, and Roma, we need to think about it now and, plan the observation.
And many of these already have been observed with
yeah,
the
but for
GRISM.
example, the faint white dwarf have not been observed. None of them have been observed with the GRISM on HST. So, for example, that's something that we are thinking about, and we should think about how many of those do we have to serve with HST? Is 5 enough, the 5 that we are doing with JWC, or we need 10, and why?
So actually, Misha's
Yes.
white dwarfs have both WFC3, GRISM, and STIS.
Piling up answers. So one of the white dwarfs in the south is variable. It's a pulsator.
That one got removed.
And over time, I think we will gonna pass over most of the faint white dwarf standards that are
So if there are
established.
If there are others to replace it with, we'd like to hear.
Yes. Coming back to calibrating many detectors, so we have 16, and what we did during PV was to place spectrophotometric standards, like spectroscopic ones, the bright CalSpec standard, but also the faint white dwarfs on, I think in photometry it was 16 positions, like a 4x4 grid per detector, and all the filters and dithering around and maintaining dither positions to see if there was some persistence effects. What helped us, or what was very astonishing to see in coming back to persistence, because we haven't calibrated, we haven't corrected for persistence for a while. We just masked it. And in our self-calibration observations, where we observed the same field near the north ecliptic pole, it's 70 dithers across the entire focal plane. And so you reconstruct the goal of that is to reconstruct the optical illumination correction, which works really well. And in addition, what we saw was a split copy of the persistence effects as well. So there is some persistence in our photometry, and it shows up really nicely in this self-calibration reconstruction. So this is definitely a method to recover photometry and all other kind of things that you miss in the upstream calibration chain.
Yeah, and to add to this, basically it's a similar approach, but maybe a little bit different in some details. During commissioning, we plan to observe a field in the Large Magellanic Cloud, which doesn't happen to have any stars brighter than 10th magnitude, by the way, so avoiding some of the persistence effects. And we'll observe it at 100 different data positions covering the whole field. This both for astrometry and for photometry. And there are about 100,000 stars in that, bright enough to get a signal noise of 50 in the per observation. So we expect to be able to do some of this flood field calibration, at least for K giants, very well. Then, of course, the question of what happens to different color stars is, that's something that has to be corrected for as well. But at least for a reference spectrum will be like that.
Having a high, sorry for interjecting, having a high number of stars is useful. In the Euclid Deep Field North, where our calibration field is, it works pretty well for the near-infrared camera. In the optical camera, you still have an issue with cosmics. We're getting there. So right now we are combining like 2 or 3 visits. And then we have a sufficiently high stellar density, but in the LMC you have, I think, an order of 100 times more sources to use, and the radiation environment is nasty, in particular now that, well, you won't launch into solar maximum, but you'll experience one eventually. It's bad.
If you're there long enough.
Two things. I think it helps to have your standard objects embedded, particularly doing surveys. Embed them in the survey within the dynamic range of the survey. So you can always come back to them when you've learned something new and redo the processing. It's there. The other thing I was saying is that with all, I mean, it might sound strange coming from me, that the degree to which we have vetted the white dwarfs in the optical and now going into the UV is not something that I believe has happened yet in the IR. So there may be gremlins waiting for us to discover.
Yeah, just on your first point, I think the supernova team is considering embedding calibration sources just for that purpose. Because you're going to be observing the same area about 100 times over the course of the survey, and it's a little harder for the wide area surveys because they only repeat a few times for each location.
Comments or questions?
So I feel I got a get out of jail free card because nobody asked about detector effects.
I think everybody's tired.
Yeah, my answer to that was,
but Stefano might be around for the next days, maybe.
Yeah, I'll be around. Yes.
Or in the next days, I don't know if you.
Stefano is always at SDEC, and it's about that time.
It is. It's definitely beer 30.
It's das beer, or you can write Stefano an email. It's a space telescope. So if you have further questions or inquiries.
I just wanted to add, he said, Stefano said we hadn't really discussed detector effects. And there's a very nice paper by Greg Mosby on the WFC3 IR, not the WFC3, the Roman detectors and detector effects that affect those Hawaii 4RG.
First author?
Greg Mosby.
Okay, so thanks very much to Stefano, Susanna, and everybody, and all the speakers today. So now in the cafeteria, we will have what we call SDA Sphere. That was the space telescope many, many years ago. It's a tradition every Wednesday. We drink beer and we chat about, science, calibration, but everything in general. So everybody's invited. There will be other people as well from Space Telescope because it's open to everybody. Please enjoy. See you tomorrow. See you later.